Now let's continue this thing. So, actually what I can say about this velocity boundary layer is that anything that's within this boundary layer, we can say that it's constant effect is significant. Yeah. Now I want you to be able to see this following equation over here. Right? What he's saying is that there's quite a fair bit of shear stress that's going on. Certain textbooks will say viscous stress. Sometimes you get to hear things like shear stress. Shear stress is given by the symbol tau. So tau over here. And that's equal to mu del u del y. Okay. Where if I were to sketch out, tau here refers to viscous or sometimes shear stress. And it has a unit of Pascal. Or sometimes you could write newtons per meter squared. And mu is your dynamic viscosity. And it has a unit newton seconds per meter squared. And del u, del y, that is your shear velocity. And it has a unit of s to the power minus 1. That is 1 over s seconds. But later on, I'm going to also have rho as my density. So that's kilograms per meter cubed. And you're going to see u infinity. So again, that's a free stream velocity. Meters per second. So anything that's outside your velocity boundary layer, that again is your velocity boundary layer, or just BL. So this word over here, BL, stands for your boundary layer. So anything that's outside, that means over here, anything that's outside your boundary layer, there's no viscosity effect. Anything that's within this boundary layer, there is strong viscous effect. And this viscous effect means that there's shearing that's going on. So you can see that this shearing arrow over here is resisting against that flow. And that amount of shear stress or viscous stress is given by this equation. And because of this presence of shear stress or viscous stress, there is a certain skin friction coefficient, Cf. And Cf is given by this formula over here. So, classically, a lot of students always ask me, hey, Dr. Tan, how do you memorize this? Well, the good news is that if I were to look at your exam data booklet, right, that equation can be found over here. Alright? This is available in your model, so please download that. You're going to be referring to this table a lot for convection and heat exchanger, which will be the subsequent topic. So please download that. I'll occasionally point out where you can find it in your data booklet. So that formula is okay. That means you don't have it. So that is your skin friction coefficient. We have to look how do we make use of that subsequently. Right now it's just definition. Now I want you to see this thing over here, del u, del y. If I have this gradient over here, this gradient where you have axis, y, and x. And if I ask you, what is the gradient for this? You'll be taking change in y divided by the change in x. Right? That's what you'll be doing. That's this gradient.
Hey, mine not complete. I need to go back here and see.
Now, instead of looking from this way, I want to turn it kind of like
Instrumentation.
90 degrees.
Blasters thing. Wow.
Don't want waste time.
Turn it 90 degrees. Where now this gradient over here is delta x, delta y over here. So it's vertical divided by your horizontal. This is the gradient. And in fact, this will be your gradient because it's sloping, it's going up. So there's a negative gradient. Why do I talk about something so fundamental? Because I want you to be able to understand this word over there. Large velocity gradient. So this velocity gradient refers to del u, del y. Note, it's not del u, del x. It's not. It's del u, del y. Del y at the bottom. So you're looking at it that way. Okay. What that means is that this gradient over here, which is del u, del y, will be large as it goes near to your plate. So this gradient over here is large. Right, you gotta look at it this way. You have a steeper gradient. Could you see it? No? It's on your head. So if you look straight on, yeah? If you look straight on, this one definitely is a smaller gradient. But if you turn your head around, it's actually a steeper gradient. Right? It's actually a steeper gradient. So this is steeper gradient. Right. Take some time to bend your head. You'll be able to see that, but if not, please consider. So that's why within this boundary layer, you have large velocity gradient. So there are two distinctive regions, that is the part that's within your boundary layer with a lot of viscous flow, and the part that's outside. And outside, we tend to say that that flow is incompressible. It's kind of laminar flow out there as well, and it's not really that, it doesn't experience any kind of shear flow out there. I think this year, mechanical design engineers are going to learn fluid dynamics. Yeah. Taught by Dr. Patrick Flaw. You just had it, I think, this morning. Have you heard about the Bernoulli equation? So over here, where there's no viscous effect, over here, that's when your Bernoulli equation holds. Right? So we need to know the velocity distribution and the shear stress that resides in the boundary layer. So we have seen that already. Now let's have a look at this other thing that's called thermal boundary layer. Now I want you to note, this surface that has a temperature Ts is at a higher temperature compared to T infinity. Yeah? So T infinity is that ambient infinity that temperature is up there. Now I want you to look at this figure very carefully now. We were talking about this part here is our velocity profile, and the velocity profile at this point over here says that it's zero velocity. If it's at zero velocity, and if this plate is hotter than T infinity up there, doesn't it mean that this water molecule in here will get Ts as the heat? The temperature of that surface, of that plate, because that molecule is not moving. If you look at the next layer, that next layer would be moving a little bit. It's able to, it's actually further away compared to the molecule that's right on top of the plate. This molecule will be at the same temperature as the plate. The one that's above it, naturally you have that temperature lower, and temperature lower, goes up all the way. So this would be the temperature profile. You have this part here that signifies, I think your figure is a little bit different than this thing. In fact, there shouldn't be an arrow in there because temperature is not a vector. So the lecturer made a mistake over here. Because temperature is not a vector, the velocity profile, that velocity is a vector. And that's why we can represent it by arrow. So if temperature is not a vector, then we just represent it by straight lines. Just straight lines will do. So now comes the interesting part. Besides the temperature, besides the velocity profile that comes up with the velocity boundary layer thickness, your temperature would also have what we call temperature boundary layer thickness. And velocity boundary layer thickness, delta, is different from temperature boundary layer thickness. That means delta may not be equal to delta T. So this part here, although it's shaped very similar to what you had for velocity, but really this part over here is del T, but it stands for temperature. Temperature, boundary, layer, thickness. And that line over there, so that was the thickness over here, that line over there is temperature, boundary layer. So del not necessarily equal to del T. T stands for temperature. So both are boundary layer thickness, but one is for velocity. So the velocity wouldn't have any subscript in. If he's talking about temperature boundary layer thickness, then there will be a subscript T. So the same goes over here. So this part, the temperature profile, is going to decrease up to this point, and anything over there that will be at the same temperature of T infinity. It is similar to your velocity profile. This line over here, this line is called your temperature profile. So just on that line over here, this one is called your velocity profile. The velocity profile and temperature profile, they have different equations behind them. Last year, we delivered that equation, but this year is not included in the notes. So it's not going to be delivered. So same as what we saw for the velocity profile, where you have u over u infinity at 0.99, 99%. The same thing goes for how do we decide when is the point that we consider that as my boundary layer for my temperature. Where is that point? That point would be Ts minus T over Ts minus T infinity at 99%. So what is T over here? T is any of these temperature that's within the boundary layer. So any of this temperature, that's T. Ts is that wall temperature, that solid surface plate temperature, Ts. And T infinity is that infinity, T infinity temperature. So Ts minus T infinity, that's essentially like the temperature difference between the solid plate and T infinity. That's the temperature difference. That's the range of temperature difference. Ts minus T. Ts here is the temperature at the plate minus any of the temperature that you're considering over here. Right? Any of this temperature. Take that difference, divide by the range of temperature difference. It must be 99% of that. Then that's the point that we consider our thermal boundary layer. Okay. So take some time to have it sink in. If I were to give you another case, this is a solid, and it has a surface temperature, Ts, and there's an ambient temperature, T infinity. If Ts now is smaller than T infinity, that means Ts is, that surface of the plate is colder. And you would still have the same kind of flow, T infinity and U infinity out there, but just that your plate is colder than this ambient temperature. The kind of temperature profile that you're going to get now, say for example this slice over here, you're going to get something that looks like that. Where this block, this line this line over here refers to the temperature Ts. So that's the temperature. It is colder, so now it's a shorter length. And T infinity remains not on the scale, but it should be the same length, T infinity. Okay. So where's the point that I consider where my thermal boundary layer is going to be? This point over here will be using this equation. So any of these lines will be temperature T. This line over here, temperature Ts. Any lines that's above this, they are all T infinity. Okay. There are a couple more videos that I'll show you. So I'll come back to this again. We'll come back to this slide again. So during lectures, if I move too fast or if any copy anything, don't worry about it. After class, come down and then I can give you access to this laptop. Let's have a look at this one. Maximum volume already.
Notice that the right here behind water stream now, you see the dimension water. This is the turbulence of the water molecules passing by. Turn the water flow up even more, you'll see the stream begins to blur the image light. Now we're back to laminar flow. Laminar flow, once again, you see my image, the finger clearly from the water stream. There's another indication of turbulence in the water flow system, though this is more maybe what's happening in the valve faucet itself. Notice the sound differences. Listen very closely. You hear the onset of turbulence as a hissing sound in the valve. You hear that hissing sound is the turbulence in the water impacting the valve. Turn the floor down. Listen closely. That's indicative of the water flow through the valve, where once again the water molecules are moving in a parallel fashion to each other, and not moving off into the turbulation before not producing any noise. Now, turbulence begins to manifest itself inside the valve before it enters.
It is cool. I think the
Passageway in the valve is much smaller